Okay guys, one more video here. This one covers Lewis acids and bases, and so I'm going to discuss what Lewis acids and bases are, and then we will start to focus on complex ions in solution, and we'll learn how to perform equilibrium constants, equilibrium problems involving complex ions. So first off, the Lewis acid-base concept is a bit more general than what we've learned about previously in terms of Arrhenius acids and bases and the Bronsted-Lowry acid and base picture. Lewis has a more general way of thinking about what makes an acid and what makes a base. And instead of involving a proton transfer reaction, the Lewis picture involves an electron pair. Okay, and so according to Lewis, an acid is a species that accepts an electron pair, and a base is a species that donates an electron pair. And in the process of trading an electron pair, the compounds form a coordinate covalent bond. It's also called a dative bond. And what that means is that the bond that's formed, the electrons that make up the bond, they both come from the same atom. And so let's look at some examples here. So in this first example, we'll consider water, which we note has two lone pairs of electrons, and we have the H plus cation, which has no electrons, and then we'll look at the formation of hydronium, H3O plus. And so what happens here is that the base, water in this case, donates an electron pair to the H plus, forming a third OH bond, and the acid accepts the electron pair. So the electron pair donor is the base, the electron pair acceptor is the acid. Here's another example involving ammonia, which has a lone pair of electrons, and H plus again. In this case, the ammonia is acting as the base. It donates its electron pair to the H plus, which accepts them, so it's the acid, and that forms the ammonium cation. These species that are formed through the coordinate covalent bond are also called the Lewis acid-base adduct. Okay, and so that's just a compound that's formed through a coordinate covalent bond in a Lewis acid-base type fashion. Here's some additional examples. In this reaction between the fluoride ion and boron trifluoride, we note that boron trifluoride is an electron-deficient species. That is, there are only 6 valence electrons around the boron. And what can happen is, in this case, the fluoride, which has plenty of electron pairs, can donate an electron pair to the boron, forming this adduct. This adduct, it's an anion in this case. And we see that the fluoride, since it's transferring its electrons, is acting as the Lewis base, and the acid, boron trifluoride, is accepting the electron pair. Here's an example involving the formation of a so-called complex ion. In this case, we've got 2 molecules of ammonia, each of them with their lone pair, and they each donate an electron pair to the silver cation. And so you form an adduct like this. And in this case, since the silver plus is accepting the electron pairs, it is the acid. The ammonia is the base because it's donating its electron pairs. Here's another example. This highlights the formation of sulfate as an acid-base adduct. The oxide ion is capable of acting as a base. It's got plenty of electron pairs. The sulfur trioxide acts as an acid, and it can accept the electron pair, leading to the sulfate adduct. And so as you look at these species here, other than ammonia, you wouldn't normally think of, these guys as being acids and bases. But the Lewis acid-base picture is a lot more general than the Bronsted-Lowry proton transfer reaction. In fact, all of these reactions, none of them involve a proton transfer at all. Okay, and so this isn't what you would call classic acid-base chemistry in the Bronsted-Lowry sense, but according to Lewis, the chemistry behind it is the same. Okay, and that's why we consider the Lewis concept to be more general than even the Bronsted-Lowry picture. This is illustrating a so-called displacement reaction. So here we have one of our acid-base adducts reacting with a different Lewis base, a stronger Lewis base, and what it does is it kicks out the ammonia, giving you a different complex ion and leaving the ammonia as a free base. The same thing is occurring in these other two reactions. Here we'll look at the reaction of the strong acid adduct HCl with acting on a base water. In this case, what happens is the water kicks out the chloride ion. Okay, so let's apply this concept to a problem. This is the complex ion formation problem. And metal cations in solution will often form coordinate covalent bonds with other molecules or anions that have available lone pairs. Okay, so through this Lewis acid-base chemistry. And so the complex ion, you have a metal with two or more Lewis bases attached to them through coordinate covalent bonds. And the example that we looked at previously was this reaction of silver plus with ammonia to give us this Lewis base adduct here. And we call this a complex ion. And the reaction that you see here has a name. It's called a formation reaction. Well, there's other reactions that are called formation reactions as well, particularly in thermochemistry. But in the sense of the complex ion formation, it's called a formation reaction, and it has its own equilibrium constant. So the Kf, which involves the concentration of the product, the complex ion in this case, divided by the concentration of the reactants. So we've got silver ion and ammonia. Ammonia should be squared because of the stoichiometric coefficient there. And if you were to take the reverse of this reaction, you would call it a dissociation reaction. The Kd is the reciprocal of the Kf. So when you're going in the forward direction, we call it a formation reaction. It has a Kf value. In the reverse direction, we call it a dissociation reaction, and it has a Kd equilibrium constant. So here's a problem involving complex ions. And so in this problem, we have a complex ion present. Its concentration is initially 0.1 molar, and we are going to let this complex ion dissociate a little bit. And what I want to point out is that I should have mentioned it on the previous slide. In fact, I'll just do it here. So Kf, you see here for the complex ion here is quite large. And so that means in this formation reaction, because Kf is so large, that indicates that this equilibrium is shifted very far to the product side. So most of the silver ion in solution is going to be wrapped up in this complex ion. In this case, we're working the problem backwards. We're starting off with the concentration of the complex ion, and then we want to calculate the amount of silver ion at equilibrium. So we're going to work this as a dissociation problem. So we're going to take the complex ion, we're going to set up an ice table. So our initial concentration of the complex ion is 0.1. Initially, we don't have any silver or ammonia present in this particular problem. Some of the ion will dissociate. That's going to produce some silver ion and some ammonia. And then to calculate the equilibrium line, we add these two lines together. So we'll have 0.1 minus x, x for the silver, and 2x for the ammonia. And what I'll note, Since Kf is so large, Kd for this reaction will be very small, which indicates that very little of the complex ion is going to dissociate, so we can get away with ignoring minus x relative to 0.1. And that's going to simplify the problem. We set up the Kd expression. Kd will be 1 over the given Kf. We have the concentrations of the ions divided by the initial concentration of the complex ion. We substitute in our approximations, so x times 2x divided by 0.1. And then what we want to do is simplify the expression and then solve for the value of x, which will give us the desired silver concentration. So rearranging this final expression, solving for the silver ion concentration gives us 1.2 times 10 to the minus 3 moles per liter, which is pretty small with respect to the 0.1 molar concentration of the complex ion itself. In this problem, we have it's a different type of complex ion problem, and it's a bit more complicated. So here, what we have is we have an amount of silver present in the solution. Okay, and so you can take this 1 gram of silver nitrate, and you can convert that to moles of silver ion present, and then divide by the volume, and that's going to give you a concentration. So we know the concentration of silver that's available. But then there's also quite a lot of cyanide present. Okay, so 10 grams of potassium cyanide. And what's going to happen is the silver ion is going to react with the cyanide to form a complex ion in solution. And what they want us to do is to calculate the amount of free silver left over in the solution. And the way that I typically work these problems is I solve them backwards. That is, what I do is I take the silver ion, and I'm just going to assume at the beginning that all of the silver ion is tied up in that complex ion. And the reason I do that is because the Kf, the equilibrium constant for the formation of the complex ion, is so large that essentially all of the silver, almost all of the silver, is going to be tied up in that ion. So why don't we just start off at the bat assuming that that's what's happened. So you take the concentration of silver that you have available, and then you just say, okay, that's going to be the initial concentration of my complex ion, and then I'm going to work this as a dissociation problem to figure out how much silver I have at equilibrium. Now there's a few tricks along the way. So the first trick in this problem is figuring out how much silver complex ion do you actually have. And so again, it's converting that 1 gram of silver nitrate to moles of silver ions and then divide by 1 liter. We're going to set that to be the initial concentration of the complex ion in our ice table. Now initially we'll say, okay, there's no silver, it's all tied up in here. But then for the cyanide, you have to take into account that when you put all of the silver in the complex ion, you consumed some of the cyanide in the process, right? You see the cyanide is present here in the compound. So you take this 10 grams of potassium cyanide and determine the number of moles per liter that you have of cyanide, okay? And that's going to be 0.154. And then what you need to do is subtract from that the amount of cyanide that reacted to form the complex ion. And based on the stoichiometry of the compound, that's going to be 2 times the number of moles per liter of the compound itself, right? Because there's 2 moles of cyanide in there for every 1 mole of the complex ion. So I subtract off minus 2 times 0.59 times 10 to the minus 3 gives me a starting concentration of cyanide of 0.142. Okay, so the tricky parts are really in this first line of the ice table, figuring out what the initial concentrations are. From here, you just assume a small amount of the complex ion will dissociate. That's going to give you some free silver, and it's going to give you back a little bit of cyanide. So then you add these 2 lines together. You get this expression for the complex ion at equilibrium, x for the silver ion concentration, and then 0.142 plus 2x for the cyanide concentration. Set up the Kd equilibrium constant expression. Kd is going to be 1 over the given Kf value. You've got the ion concentrations in the numerator, and the complex ion concentration in the denominator, and then you substitute in the equilibrium concentrations, so x times 0.142 divided by, and we're going to make our approximation here as well. That is, x is going to be so small we can neglect minus x relative to 5.9 times 10 to the minus 3, so we just have that in the denominator. And then what you want to do is solve this equation algebraically for the value of x. That's going to be equal to the silver ion concentration, and you get a value, in this case, of 4.2 times 10 to the minus 23 moles per liter, which is very, very small. There's essentially no free silver in this solution. Okay, so I will stop this video right here.